Hey, you guys. Welcome to Friday. Well, I'm home with the baby today, so you're going to get digital me once again. So you got me 2 days in a row. Sorry about that. I left kind of midday yesterday, and then today I'm back again. But I have brought, for your viewing pleasure and auditory pleasure, another video from me, which will be posted. I'll put it on Google Plus too, so you can see it there at your leisure. Now, where I didn't get a chance to get to is the remainder of the examples in the notes that I gave you, and that'll help you finish up the worksheet that I gave you as well. So here's a couple things you have to take note of. This problem is, what we're going to see is the signs of the coefficients a, b, and c can be determined by looking at this kind of graphed polynomial. The idea is, when I show you this Taylor polynomial, is kind of layering on additional factors from a known function. So that's why it's kind of tailoring it, fitting it to your graph. You start with the constant, which is just locating it on the graph where it is, where it's centered at. Then you get the first derivative. That b term has to do with the linear, actually it's the equation of the tangent line. The a plus bx is the equation of the tangent line at the center for the polynomial in question. So it gives you a tangent line right there. And then the next one, it's squared. It's talking squared, remember, is that second derivative term, where the c coefficient goes with a second derivative, and then also divided by a factorial, a 2 factorial. Well, second derivative has to do with concavity. So what we're doing is, first we start with a point, then we layer in the slope of the function, then we layer in its concavity, and you see we're getting more and more information on how to morph this polynomial to the given curve. So knowing the sign actually is very helpful. That is, positive or negative can be a big part of deciding, what this function looks like. So it's a bit of a theoretical, kind of hypothetical game. It's just a mental game that we play. Something AP examiners really like to run you through. It's just one of those fun type of problems. So here we'll start with f of 0. The function itself, what you're going to get, that a term always comes from f of 0. So if you haven't figured that out yet, good to know. That a term will come from just doing the original function at the center. So got that, located it, and we're centering at 0, so it's technically a Maclaurin series. You could call it Taylor series too, centered at 0, but Maclaurin if you want to. Then what that means is, well, it's positive. It's above the axis, so we do know that sign, so a has a positive sign. Then there's b, first derivative. If you take and find that coefficient, which is f prime of 0 over 1 factorial, if you look at that, it's the slope. The first derivative is the slope of the tangent line. That's what this boils down to at that location, and we can see it's positive. Draw a little line in there. Positive slope, so we know it's greater than 0. Got that sign. Next one is c, the coefficient for the f second derivative, and I put f2. Could put the Roman numerals as well, probably should have, at 0, and that's concavity. Now we do have the divided by 2 factorial. We know that's 2. When we're talking just sign here, all we're saying is, well, looking at concavity divided by the 2 factorial, which is just 2. The concavity, in this case, facing down, that cupping down is a negative number for the second derivative, would be concave down. So we know the sign of this one is negative. So just to recap, that constant a term, the y-intercept, if it's centered at 0, slope we got from the first, the b coefficient, because it's f prime, and then concavity comes from informs divided by 2 factorial, tells us the sign of that third term, and we know it's less than 0 because it is concave down. There you are. We've justified it, shown it in the graph, all kinds of stuff. So it's amazing what information you get just by looking at the graph. We know a lot about our Taylor polynomial approximation, even just that way. Next, so 8, a, b, and c. Let's bring up some neat things we've done. We've talked about the sign of x and how we can do the Taylor polynomial for that. Kind of skipping terms, alternating. If you want to go back and look at that in your notes, you'll see where that came from. I just wrote it out here to the 9th degree. What we can do is, the cool thing about that is we could actually do the same for cosine. Go find the Taylor polynomial, take 9 derivatives, and then get those coefficients, divide them by the appropriate factorials, take it times x to the appropriate power. All that work. Or we could just take the derivative. Remember, with these series, we can actually take derivatives and integrals to produce new series or sequences. We'll just say series, and these are Taylor approximations. What we'll do is take the derivative of sine of x, first term, derivative of x is 1, and then take the derivative of the second term. We'd get 3x squared over 3 factorial. Factorials are constants, so you can just leave it in as though it's a constant. And then the next one, 5x to the fourth over 5 factorial, and so on. So I think you got the idea. So you just take the derivative, and there you go. There's our Taylor polynomial for cosine of x. So you really have to know sine of x, and then you can take the derivative to get cosine of x. Ideally, you'll memorize both of those. Those are two really important foundational polynomials from which we can kind of modify to make the others, hence these three problems. So now, let's go ahead and take a look at cosine. I'm going to simplify it a little bit. The thing that you may not know is factorials. If you don't know them very well, factorial means 3 times, like 3 factorial, 3 times 2 times 1. So if I have 3 divided by 3 factorial, take a peek here at the top. If you have that, you can actually cancel the 3's, and it ends up just being 2 times 1, which is 2 factorial. Same with 5 factorial, 5 over 5 factorial. That's just 5's cancel, you get 4 factorial in the denominator. Continue that, and then the cosine of x simplifies to what you see here. So now, look at those derivatives. Aren't those cool? All right, line them up, rock and roll. Now, what we're going to do is modify each one of these to come up with the polynomial in question. We're trying to approximate sine of 2x and x cosine of x. So we'll get there. Oh, wait, let's just do e of x first. We did that the other day, right? We took the derivatives. E's derivatives of e to the x is always the same. If we center at 0, we always get 1 for the coefficient. So there's the nice Taylor polynomial for e to the x. Very nice. Another one you should have in your back pocket. All right, so let's start modifying. Sine of 2x means put 2x in for x. So here we are. Just leave some space, take out the x, put 2x in its place. Maybe a little simplifying, so hopefully that's clear. Simplifying things like distributing the power, so you get 8. 2 to the third is 8, 2 to the fifth is 32, 2 to the seventh is 128, and so on. And you can pull that factorial out front as well, so you can just have a very crisp coefficient. And then you're welcome to, if you want, to bust out some common factors in the numerator and denominator on that coefficient. Like 8 is 8 over 6, because a 3 factorial is 6. 32 is over 5 factorial. Check this out. You can cancel the 4 times 2 with 8 in the top. So basically divide them both by 8. And you'd have 4 over 15 if you want to simplify that second term. It's up to you. It depends on how much work you want to do simplifying. Now, x cosine of x, I bet you know what's coming. What's multiply through by x? This one's a beauty. Everything goes up a degree. 1 becomes x because you're multiplying by x. That's it. That's the end of story there. Very clean, very crisp. It's nice to, once you have 3 of them down, then you could just mess with them to get the others. All right, 4e to the x squared. Look at the modifications. We're multiplying by 4 and replacing x with x squared. The only thing to be careful about is when you replace x with x squared, the first term stays is just 4 because we're centering at 0. E to the x squared, if you want to take a look at that could be a little tricky as you go along. All right, just to keep it kind of clean, I'm just going to let you peek at this, see if there's any simplifications that throw you off. Just notice when you put x squared in for x, you have things like x squared to the second. Well, that's x to the fourth because you multiply the powers. X to the third, x squared to the third because you put x squared in for that x where it was cubed. You get x to the sixth, multiply powers. 4 over 4 factorial, you can cancel the 4's and just get 4 over 3 factorial. Just take a close look at that and let me know if you have questions about that. Take care. Have a good weekend, guys. See you soon.